All right, thank you. So I'm going to start with the Snails theorem, which basically says if you want to study immersions from one manifold into another manifold, well, let's consider a weaker problem, namely formal immersions, which are pairs just some function and some function on the tangent bundle covering the function on the base, where capital F is injective. Whereas here I require that df is injective. So the theorem is that this is a homotopy equivalence. If m is less than n. So the only obstruction if you want to embed m into n, is just being able to solve this much more easy to solve problem of linear algebra on the tangent spaces. So this is an example of an H principle, H for homotopy. And so you might classify, if you're studying a certain problem that can be phrased in the language of differential topology and differential relations, you might consider, let's say a problem is rigid if it doesn't have such a if it's not governed by homotopy data, and it's rigid if there's obstructions beyond just doing it in a weak homotopy sense. So symplectic / contact topology. So this lies, is on the borderline on the interface between rigid and, say, flexible phenomenon. Okay, so before I give examples of what this sentence means, or giving rigid and flexible things, let me just remind you of what a contact structure is and what a symplectic structure is. So a contact structure, so you have an odd dimensional manifold, and you have a hyperplane distribution given you as the kernel of a one form, where alpha is a one form, and you have this relation. Which you can interpret as meaning that this distribution is maximally non-integral, where integral would be if just alpha wedge d alpha was identically equal to 0. And symplectic is where you have an even dimensional manifold, and omega is a closed, non-degenerate 2 form. So examples, so these structures are very flexible, and that you have the following fact, that there's no local invariance in contact / symplectic geometry. And what I mean by that, we have the following local models that any symplectic manifold or any contact manifold will be isomorphic to the following forms. So the contact form, you have R2n plus 1 and you have kernel vz plus some ri squared d phi, where these are polar coordinates on copies of, so you have one individual copy of R, and then you have n copies of R2, where these are the polar coordinates there. And you have this model where omega is some dxi wedge dy. So these are locally, this is all there is locally. So any attempt of replaying, like doing Riemannian geometry where you study curvature is thrown out the window. So there's no local invariance, but starting with, coming from Gromov's method of pseudo-holomorphic curves in the mid-'80s, people began to construct global invariance that would give you rigidity results, but it only on a global setting. So this is flexibility. So we even have there's the following H principle. So it's that if you look at contact structures on a manifold, embed into formal contact structures, this is a homotopy equivalence if M is open. So a formal contact structure, just like a formal immersion, is you replace d alpha with just some 2 form. And if you can solve this for alpha wedge omega to the n for some 2 form omega, that's a formal contact structure. However, we have rigidity. So this is flexible. So then there's the following rigidity result by Ellie Ashberg, Gromov. And it says the following, that you have the following failure of a homotopy principle, where you have, if you do this rel, if you looked at this rel boundary, so contact structures, boundary of M into pi 0 of formal contact structures, M boundary of M. Where contact structures, what I mean by this is C on M such that C equals, this is some fixed contact structure near the boundary of M. And here I have a formal contact structure that's near the boundary is an actual contact structure, and it equals Cm. And so the rigidity result is that this is not an isomorphism. And it follows, you can prove this using the fact that the set of contactomorphisms is C0 closed in the set of diffeomorphisms. OK. So I'll just write this here. So then we have the following flexibility of overtwisted contact structures. And this is myself Ellie Ashberg and Murphy. And it basically says you can get this if you restrict the contact structures here to a special class of contact structures called overtwisted contact structures. So you have so I'll write it this way into formal contact structures. On M is an isomorphism on pi 0. So as long as we define a special class of contact structures called overtwisted contact structures, where we can prove that this inclusion gives you an isomorphism on pi 0. And so in particular, that means the following, that if you have a formal contact structure, there always is a contact structure that sits in that homotopy class of contact structures. And for these contact structures are also special in the sense that if you want to prove two of them are equivalent, you just need to show that their equivalent formally is almost contact structures. So I should say that this was proved in the case of 3 dimensions by Ellie Ashberg in the late 80s. So I guess the theorem was mainly kind of finding the right notion of what overtwisted should be in higher dimensions to make the proof generalized to go through. And so let me just give a slight idea of what overtwisted contact structures are. So there's basically a special model of a 2n-dimensional disk with a germ of a contact structure on it. And if it embeds into your contact manifold as a contact embedding, so if there exists, then C is overtwisted. So this is a germ of a contact structure near this disk. And I can't draw higher dimensions that well, but I'll just say that I'll just draw the disk in 2 dimensions. So if you take D2, it looks like this, and it has the following property that it looks, I'm going to draw these lines that look kind of like this, where these lines are the intersection of the tangent spaces of the disk intersect the contact structure. Yeah, and it's actually tangent on the boundary. And our definition, I think part of the difficulty and why there was a gap between when Ellie Ashberg proved this result in dimension 3 and now is because there's 2 ways to generalize a 2-dimensional surface in a 3-dimensional manifold. And many people seem to try an n+1 dimensional thing and a 2n+1 dimensional thing. But we did a hypersurface. And so our definition of overtwisted disk, generally, it's different but equivalent. It's different looking, but equivalent to Ellie Ashberg's definition in 3 dimensions. And it's clear how it's a generalization. The higher dimensional version is a generalization of the 2-dimensional version. So that's